Is it like my immediate on Zoom?
Yes, it does.
Okay. I'm gonna hack in most of it because I still got the reading controls hidden.
I'm not sure if the microphone is actually working. It doesn't have
Yeah, last time we did it, someone said that the sound wasn't so good, so I just unplugged it.
All right. And plug it back in.
Oh, did we just use the? No, I meant unplug it, but.
Oh, there. Okay, it seems to be working now. Excellent.
Well, thank you everyone who's here today. We are excited to be at Claremont, Science Celebration on tour, this fall, and next month we're gonna be at the West Branch Library. Tonight we're at Claremont. I'm going to start us off with our land acknowledgement, and then we'll have, I'll introduce the program, and we'll have the Science Bubble team introduce tonight's speakers. Thank you so much. Berkeley Public Library buildings are built on the territory of the Greenpoon within the homeland of the Chochenyo speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley and throughout the East Bay since time immemorial. The library recognizes that Berkeley residents have and continue to benefit from the use and occupation of unceded stolen land, and we pledge to recognize the permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strength of the Ohlone people and their culture. The Berkeley Public Library is committed to helping create a more just and anti-racist society, and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. This is a living document that was co-written by Ohlone cultural leaders Vincent Medina and Louis Trevino and the Berkeley Public Library. And if you're interested in learning more about Ohlone culture, our library does a regular, almost monthly program with Cafe Ohlone. Tomorrow, we're visiting Cafe Ohlone and learning how to play an Ohlone dice game. Usually they make a treat out of Ohlone ingredients and using Ohlone techniques. It happens every third Wednesday of the month around 3:30 usually. So that's Cafe Ohlone. You can see that on our events calendar. So welcome to Pocket Science Bubble. This is a monthly seminar series that aims to share new research findings from graduate students and postdocs at UC Berkeley with the general public to create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic that they find really interesting. The organizers are 2 graduate students at UC Berkeley, Kaylin Swong and Daniel Bray. This program happens every 3rd Tuesday of the month at 5:30 p.m. at the library and on Zoom. If you're interested in checking out past seminars, you can visit their website and their YouTube page. Highly recommend the YouTube page. Just has an archive of so many incredible programs. You can also sign up for the listserv in order to keep abreast of upcoming topics. And yeah, check us out online. All right, thank you.
Awesome. Yeah, thank you so much for being here for tonight, Popping the Science Bubble. So as Kelsey mentioned, we host Popping the Science Bubble the 3rd Tuesday of every month. And our next seminar is going to be at the West Branch while we are doing our tour of all the different branches. And so we aim to bring to you talks from researchers from a wide variety of departments to share their interesting research with you. We will be showing, as Kelsey had mentioned, a QR code where you can sign up for all the emails and understand where, when, where all of our seminars are going to be happening. So for tonight, we're very excited to have both Riley Owen and Eleanor Greenspoon presenting for us tonight. And so this is an open format talk. So if you have any questions, please raise your hand and the speakers will call on you to ask your question when they see fit. If you are currently on the Zoom, then you can please use the Q&A function. And by the end of the talk, we will read your question aloud to the speakers. And so to start us off, tonight's first speaker is Riley Owens, who grew up in Cincinnati and earned a Bachelor of Science in Astrophysics and Physics and a minor in Mathematics from the University of Cincinnati in 2022. And then he joined the Department of Astronomy at UC Berkeley as a graduate student just this year. Outside of his career, he is a local advocate for housing and transportation and spends a lot of time thinking about restoring majesty to American cities. So please take it away, Riley.
Awesome, excellent, Daniel. Thank you so much for the introduction. Thank you to the library for hosting us and for our organizers for putting all this together. This is really awesome. Okay, so I'll be brief with introductions, but my name is Riley Owens. I just joined the astronomy department at UC Berkeley just this fall. Excited to share a little bit about this phenomenon that astronomers call gravitational lensing, because it's really my primary topic of study before I came to Cal. So I guess I should be using my clicker here. Maybe. It was just working earlier.
Click on the presentation and then let's bring it back.
Okay, yeah. I don't want to change, but there we go. Okay, so I assume that most of you have probably seen or used a magnifying glass before. And you've noticed before how it makes objects appear larger than you actually know they are. Okay, good example here being this pen. So that doesn't show up very well on the board at all. That's okay. Anyways, but I mean, you can tell how the pen is much larger through the magnifying glass and on the background table there. You might have also used it to, for example, concentrate the light from the sun to start a fire if you're a pyromaniac, maybe. If you were really sadistic as a child, you might have turned it into a death ray for ants. But just like how an optical lens can bend and concentrate light, so too can mass. So this is a basic prediction of one of Einstein's theories, theory of general relativity. Before adding a mass here, you see the object directly where it actually physically is. There's a direct line between you and that object. But after you add the mass, for a moment, yeah, here we go. So that trajectory changes, where you appear to see the object. Because that object has mass, it's bending the space-time around it, which causes that light to deflect, okay? So you don't actually, under the presence of that mass, see the object where it actually physically is. Give you an example, try to illustrate. So if you were to trace that light ray directly back in a straight line, you'll see it somewhere else on the sky than where it actually started here. Okay, so you see the apparent position of the image in a different place than where it physically is. It was in this manner that astronomers first found direct evidence that general relativity was a correct description of nature. So during the 1919 solar eclipse, they were able to observe distant stars that are really close to the sun on the sky. Okay, so normally, because they're very close to the sun on the sky, you wouldn't be able to see them during the day because the sun's really bright and masks out all of that. And what they noticed when they observed these stars is that if they would compare them against where they expected them to be, it was fairly different, just slightly. Enough that they were certain that it was the true difference. And that's the deflection of the light, like we just saw earlier, passing near this massive foreground object, in this case, the sun. Again, this is a direct picture of the 1919 solar eclipse. You can even see a prominence from the sun then. And while mass can just deflect light of objects passing nearby, you can also think of a more extreme scenario. If, for example, you have an object that is almost or very near to directly behind that massive foreground object, then as these light rays spread out from that object, they're gonna pass on either side. And they can bend around back to you on both sides. So if you do this exercise again, where we trace back in a straight line, where it looks like that light ray is coming from, you get multiple images of the same object, one on either side. So we actually have a picture of some of Einstein's early calculations regarding this effect. The archive of his notes and letters and such. But when he made these calculations with his new theory of general relativity, he found that it should be unobservably small. Okay, he was specifically thinking of two stars that are almost perfectly aligned. In fact, in the article that he published about this effect, he said specifically, of course, there is no hope of observing this phenomenon directly. In physics and astronomy, I feel there's often a tradition of making a prediction of a non-detection and detecting something anyways. And this was the case here as well. And he said this primarily because stars are just too small. They aren't massive enough, and they also aren't physically large enough on the sky to get those really chance alignments. Because on the sky, most stars to us just look like extremely tiny specks of light on the sky. And if they did align those multiple images, because on a relative scale, stars are really that massive in terms of different astronomical objects that we know about, they don't actually cause that much deflection. Okay, so those multiple images would be really, really close to your foreground star. There's no way you'd be able to make them out. But we can think instead, what if we had objects that were significantly more massive than stars? Anybody know an example of one of those?
Black hole.
A black hole, yeah. So we know about supermassive black holes. They can be millions or billions of times the mass of our sun. Any other objects? Doesn't have to be specific objects, but amalgamations of them. Galaxies, exactly, right. So in 1936, when Einstein first published this brief paper about this effect, the concept of other galaxies, apart from our own, was still a really new one. Only in the last decade or so was this really taking off. So he thought about it in terms of stars on stars. Okay, but if we think about if galaxies could cause this instead, and astronomers quickly realized that this might be the case, that resolves a lot of the problems we have with actually observing this. Okay, because they're much, much more massive. You get a lot more deflection, so it's well separated from your actual foreground object. You can separate the two. And because on the sky, galaxies look much larger because they are physically larger, then you don't need such chance alignments to make this happen. Okay, so that gets rid of both of these problems for us. And indeed, about 4 decades later, after that paper, astronomers found the first direct observational evidence of gravitational lensing. Okay, so what you're seeing here is two identical images of the same quasar. So just to parse this quickly, quasar is the really bright disk around a supermassive black hole. Okay, and it's difficult to make out, but there's this little bump here that's kind of attached to one of the images. That's actually the foreground galaxy there. Okay, quasar is really bright, so it's difficult to make it out. And that's the thing that's actually doing the lensing, splitting that quasar up into two images on the sky. And the exact shape of the lens galaxy on the sky actually tells us a lot about the specific mass distribution of the thing that is doing the lensing. So here's just a couple different examples we see pretty frequently. If you have a spherical mass distribution, like in the top here, you expect to get something called an Einstein ring. Okay, so this is where your background galaxy or object or whatever it is, could be a star too, is actually working to a ring around that foreground galaxy. Okay, so this big bright dot here, that's the foreground galaxy that is doing the lensing, and then wrapped around it into a ring is the background galaxy behind it. If you have an elliptical distribution like in the middle here, you expect light to instead kind of concentrate around the cusps of that elliptical distribution, so that it concentrates into 4 images around that central foreground galaxy. Call that an Einstein cross. You might be noticing the pattern here. And the other really common case too is for a galaxy cluster. It's a little bit more complicated because clusters are very large assemblies of galaxies that each have, kind of their own spherical or somewhat elliptical distributions. And typically what we see, and it's a little difficult to tell here, but I'll show you an example soon, is that galaxies appear as very large arcs around that cluster instead. Again, here's just one example of a galaxy cluster lens. So most of the galaxies that are in the cluster are around here. And then out here you have a background galaxy, this little streak here. It gets stretched out into that arc shape. And these arcs can get significantly larger than this. That's just one example. But as astronomers, leveraging that gravitational lensing is really powerful. Okay, because it's directly magnifying that background galaxy. And it's really the only way we have to see, yeah.
And just really quickly on, this is the pure science fact, but when you see like the doubled image of the quasar or another star in
Yeah.
it, how do you know that that's the same object in the sky?
Yeah,
How do you actually identify that those are the same underlying quasar?
yeah, that's a great question. And this is something that they openly postulated in this discovery paper. Is it a twin quasi-stellar object? Is it a twin quasar? So 2 different physical things, or is it gravitational lensing? Usually how we distinguish this is by taking a spectrum of either image. Okay, so if you divvy up the light that you get from that background object into the constituent wavelengths, and you look at how bright it is at each wavelength, if it's the same thing, it should look identical, up to some, maybe brightness factor, because the images aren't always the same brightness. But the point being that if they look the same in that way, then you can be pretty confident that they are physically the same thing. You can also measure something called the redshift, which is basically a proxy for how distant the thing is. So if you see 2 things that have a very similar redshift, again, you're trying to decide if it's lensing or not, but you know that they're about the same distance apart, sorry, distance away from you, then you can be pretty confident that they're actually the same thing. But you can also look for example, the thing that is doing the lensing. It's really easy to do, for example, with clusters. It's harder to do here because it's not as resolved from those quasar images. Okay, but we really like gravitational lensing as astronomers because it allows us to really look at the guts of galaxies in a way that we can't otherwise. We know that galaxies are not just these uniform, homogeneous things. They have building blocks. Okay, there's stars and gas and dust and nebulae in galaxies. And it really allows us to start to answer for those different components. How old are they? How are they moving within the galaxy? Are they forming stars? Is it dusty? What kind of stars do they have? And in the unlensed case, it's like right here, they just look like dots. And you can't start to break them up in their insides. Okay? And you have to kind of relegate yourself to asking, what do things look like on average in a global sense? But we know that galaxies are not, they're an amalgamation of different things that can vary quite a lot. It's important to know how those things interact with each other to know how that galaxy is going to evolve. Okay, now I won't spend a ton of time talking about this, but we can even detect lensed supernovae. Okay, so you might know that a supernova is a really bright event that occurs toward the end of a star's life. It becomes extremely bright, sometimes even brighter than the rest of its host galaxy combined. And we can make out individual supernovas, so these little tiny dots here and here. That's a supernova in that galaxy going on. Okay, and that's at some extreme cosmological distance that otherwise we would never be able to see them. So it allows you to ask what these things look like throughout distance and time in the universe. Yeah.
Just going back to that lens supernova, that it's it corresponds to kind of a dying star in a galaxy. But the mass around which the light is kind of getting lensed is the galaxy itself. Yes, or is it a different thing?
So here in this arc that these
Yeah.
images of the supernova are kind of embedded in,
Yeah,
that is the background of the galaxy that's getting lensed. So you're seeing in this big arc around it, the host galaxy that the supernova is in. Okay, and you can see here, this is the cluster lensing in the center here.
so the thing that's, sorry, Murder.
Yeah.
Thing that's being lensed is the light from the gallery and not from the supernova.
Both.
Okay,
Both. So what can happen sometimes if you have certain arrangements of that lensing mass is that really tiny pieces of that galaxy can get blown up to extreme magnifications. So this galaxy overall is still being magnified somehow, maybe by a few tens of times brighter. But simultaneously, a little portion of it is also getting magnified by a much more extreme amount. It also helps us that supernovae are just intrinsically very bright, so you don't need very large deviations in the lensing to see them in really distant galaxies if those galaxies are lensed. So there's some like differential magnification across the face of the galaxy in the background is not the different parts of the galaxy aren't necessarily being uniformly magnified. Okay, I mean, touching on this topic, sometimes these lenses can produce really extreme magnification, as much as thousands of times brighter than you would otherwise see these things. And this is how we actually found what we think is the most distant star we can see, called Earendel. If you're a Lord of the Rings fan, that name is not a coincidence. We know that Earendel is more than 20 billion light years away from us. But because it's so extremely magnified by thousands of times brighter, we can still see it with modern telescopes. And if you were to compare it just to your eyes, for example, on a really dark, excellent night sky, you can see stars that are maybe like tens of thousands of light years away. Okay, so without gravitational lensing, this would be completely impossible. We can ask ourselves things like, when we see individual stars like this, how do we think that stars change throughout time in the really distant universe? Are they made up of the same, mixtures of elements throughout time? How do they evolve? So on and so forth. And this would be totally impossible without lensing. You would never be able to see this individual star. Yeah.
This might be unrelated, but
Yeah.
like sometimes I see a lot of stars like twinkling. Is that related to anything with lensing, or is that just the tech?
So typically, the lensing that you see twinkling that you see with your eye, if you just go up and look at the night sky, that's due to atmospheric turbulence. Okay, so it's the Earth's atmosphere. However, on top of I guess what I would call the bulk lensing, you can get tiny variations in the magnification, especially for really small objects. It's shuffling slightly inside the galaxy. The mass of the lens itself is moving around a little bit, so that can change the magnification slightly. So you can see tiny differences in the brightness because of that. We call it micro lensing, and I'll touch on that later.
I guess sorry.
Yeah.
Like I wanted to ask that question is because like that star in the middle looks, or I don't know if it's a star, but it has like the
right here.
yeah, like some six-fold.
Yeah.
Like, is that what you would consider twinkling, or like is that
So,
completely different?
Yes, these spikes here, this is what we call a diffraction pattern.
Okay.
It's just a consequence of that it's not a perfect instrument that we're looking. So for example, if at night you go and look at a street light and you kind of squint your eyes, you kind of get those spikes on the street light, right? That's a consequence of your eye not being a perfect detector. The street light doesn't actually have those spikes. I mean, you can go closer to it and it's very well shaped. So those spikes aren't real. It's just a product of the detector that we have. Yeah. Okay, I think, how am I doing on time? Am I doing okay? I have some overflow slides I can go through. Okay, perfect. Yes, I told you a little bit before about how Einstein made these predictions about the observability of gravitational lensing. And that it wouldn't be possible to see a star-star lens event. That's actually not entirely true. Because we may not be able to make out those multiple images, because you need really high angular resolution. But you can make out the changes in the brightness. Because remember, there are multiple images there. You just can't distinguish them from each other. Okay, you're getting more light than you would otherwise from that lensing event. But here's just a quick example. You have a rogue exoplanet just kind of floating out in space. It got lost somehow. And it crosses in front of a background star. That itself can cause some lensing. Okay, so that if you had an extremely high angular resolution telescope, you can make out those two images. And because you're getting those double images, because you're getting more light than you otherwise would, you see a increase in brightness of that background star as your exoplanet crosses in front of it. Okay, the exoplanet isn't supermassive, but it does have some mass. So it is bending space-time around it and causing that fluctuation. You can also see that change of brightness if, for example, you have a star plus exoplanet system crossing in front of a background star. And they have distinct peaks. Okay, so this increase in brightness, you have the big wide peak. That's from this foreground star passing from the background one. And it should make some amount of sense because that star is much more massive than the planet. It's going to cause more magnification, more lensing. But as the planet crosses in front of that background star, you see a tiny peak here. Okay, so it's not as high or as wide as the magnification or the change of brightness caused by the star, but it is a distinct peak, and that's because it's lagging behind its parent star, a lot less massive, so it doesn't cause as much magnification. But even these things still require very chance alignments. We haven't really, I haven't justified to you why we expect to see this despite that. But that's okay, because we know that the Milky Way has something like 400 billion stars. So even if the probability of that transit happening is extremely low, there's so many stars on the sky that you at least expect to see some of them. And they do happen with some pretty regular frequency. Okay, so what you're seeing right now is a map of our Milky Way. All these dots that are flashing here represent different lensing events across time. This is a time lapse. This is from 2016, now 2017. Now, this is not to scale. They don't actually get that much brighter here. But just so you can see kind of how these map across the sky. It's like you're getting something like several or tens of these every month in the sky. That's one way that we can also detect exoplanets. Okay, so this is the number of new exoplanets we've detected by year. In orange here is from that gravitational lensing effect. Okay, so it's about 20 years old. It's hardly a dominant way to detect exoplanets, but it is increasing in terms of its viability. Yeah.
Just to make sure that I'm following, the way that you would detect an exoplanet from a lensing event, you have an lensing event and you say, there must be some mass that's like inducing that kind of
Right.
behavior for the stuff that we know is behind it.
Mhm.
And that must be an exoplanet.
Right, so you can gauge, you can infer something about the masses of the two objects, the thing being lensed and the thing doing the lensing. Okay, if you know that it's a really high ratio between the two, then you can infer, well, it must be an exoplanet doing the lensing. Okay, because exoplanets, you know, are typically much less massive than stars. But if they're similar, then you might infer, okay, it looks like it should be a star. You can also watch, because the star itself is bright, foreground one. You can watch as it goes across the sky and know that, well, it must be a star. Actually,
So what was the radial velocity on that legend?
so what
What is the radial velocity?
Oh, so when planets are orbiting around stars, okay, to a first order approximation, we say that the star is stationary. Okay, the star itself is not moving, it's fixed, and it's just the planets moving around it. But we know from, for example, Newton's laws, that every force has an equal and opposite reaction force. So planets are actually tugging back on their host stars as hard as the star is tugging on the planets just due to its force due to gravity. Star doesn't move very much though, because it's way more massive. Okay, it's the same thing if you jump. Okay, you move, but the Earth doesn't really move because the Earth is many orders of magnitude larger than you, has a lot more inertia. Okay. But that wobble that you get from the star slightly moving because the planet's dug on it, it's large enough that you can measure what we call a Doppler shift. Okay, so you can measure relative velocity of how quickly the star is moving along your line of sight. If it's moving in a really periodic fashion like that, you can infer that something has to be orbiting it.
Thank you.
Yep. Okay, no, I'm probably over time at this point, but I just want to super quickly mention this kind of wacky idea using gravitational lensing for a new telescope. Because it's not even entirely true that we couldn't see the gravitational lens from our own sun. Okay, so if you send out a telescope to about 600 times the distance between the Earth and the sun, way out in the farthest reaches of the solar system, you would get to the focal point of the sun's gravitational lens. And if you put a telescope there, you could see things with extraordinary resolution on behind the sun, wherever you are, wherever you put that telescope, whatever's behind it. If it were a planet, for example, okay, maybe a few hundred light years away, Earth-sized, you could reconstruct an image looking something like this on the right here. I'll show it in a second, but really excellent, like unfathomable images of planets around other stars. The Einstein ring around the sun might look something like this kind of pale blue ring here, if we were to block out the sun with a little gadget on our telescope. And then you can use some equations from general relativity to basically unwind that ring into how it will look if it were unblurred. And you get some really grainy and kind of blurry image, but you could get down to like making out distances of like 25 kilometers or something like that on this planet. Okay, final slide here, just to give an idea of how like incredible this would be as a technological accomplishment. So this big orange kind of donut shaped thing, I'll zoom out, zooming in. This big orange donut shaped thing, that is an image of a black hole that we have directly taken a picture of. It would be about the size of a donut on the moon, on the sky. That's how, if you were to look at that black hole, that's how large it would appear to your eye. If we compare that to the size of a planet orbiting a few hundred light years away around some star, that would be the apparent size compared to your black hole. So something like 100th of the apparent size that you would still be able to make out. So significantly higher angular resolution than the highest resolution images we've ever taken. The only downside is that it's going to take a while to get out to 600 times the distance between the Earth and the sun. So you better start early. And you also need to carefully pick where you decide to put your telescope. Because once it's out there, first of all, you can't, if it breaks, it breaks. You can't go out there and fix it. But it's also going to take a really long time to switch between targets. Okay, to move around the sun, to bring whatever it wants to look at directly behind the sun. Okay, so I'll scroll back to my question slide. I'm happy to answer any more questions.
Question.
Yeah.
So when you say angular resolution, first thing that I thought is like 360-degree camera. Like, could you put like a lens on top of our instrument, and then it would like allow us to see in more directions at the same time?
When you say like an optical lens, or
Yeah, like, you know, a 360-degree camera is usually comprised of two large lenses that extend a field of view to be, you know, 180 on one side, 180 on the other side, and like an ideal case. So if you took one of those like hemispheres, and then you put it at the front of like an instrument, could you increase the angular resolution?
so angular resolution is not necessarily connected to the field of view. So when we talk about angular resolution, we basically mean our ability to make out to things on the sky. Okay, so really poor angular resolution is tell that two objects that are really close to each other are actually two objects. It'll just look like one single object that's kind of blended together. You know, that's going back to here, this is a good example. If we had a higher angular resolution telescope, it might be really obvious that this foreground galaxy is completely separated from that background quasar. You might be able to directly see the empty space between them if we had a higher angular resolution telescope.
Would it be solved by like a stereo?
Uh,
Two telescopes, both pointing at the same object, but kind of sort of offset. Could you use that to?
So we can use something called interferometry. So if you point two or more telescopes at the same thing, and you have a really good idea of the exact distances between them, you can actually functionally make a telescope that is the size that has a basically collecting mirror, functionally the size of the distance between the two telescopes. So for example, I showed you the very last slide here. This picture of that black hole, okay, that was not taken with a single telescope. It was taken with a bunch of telescopes that we basically combined using interferometry across the Earth to make functionally a telescope that is the size of the Earth. We wouldn't have been able to get such a high angular resolution image. Anyways, yeah.
I apologize if you already said this, but what's the
No problem.
diameter of the black hole in this image?
Oh, so that's a good question. I don't know. Yeah, I'm not sure. So this is either. I know that one of the images that we have of black holes is the Milky Way, and that one is about 4 million solar masses. So it would probably fit within like a solar system, like something on that scale. It's not like light years across. It's not like smaller than the size of the sun or something. The more massive a black hole is, the larger we expect it to be.
Could you talk about when you get images from the telescope,
Mhm.
how do you identify lensing events? Do you just see where it gets brighter?
Yeah, that's a great question. So we're thinking of micro lensing specifically, just these brief flashes where things get brighter because of some sort of transit in front of it. This is a really difficult problem because if you want to identify a change in brightness, that implies that you got to watch it for some amount of time, right, to know that it got brighter. As astronomers, is that we really like things with a really wide field of view. Okay, so we can take a bunch of really large images of the sky every night, and then night to night compare things, basically, and see, did this thing get brighter, did it get fainter, etc. If you're familiar with the Vera Rubin telescope that just opened this summer, that's basically the entire point of that telescope. So every night it's going to take a picture of basically the entire southern sky that it can see. And it'll be able to detect like almost hour to hour in some cases, changes in brightness. So you can do things like find new asteroids, find these microlensing events. We also have things called variable stars that can change in brightness on short timescales that allow you to detect things like that. Yeah.
Awesome. If there are no more questions, then let's thank Riley again.
Thank you very much for the opportunity.
Swap. Oops. Oops.
You want to mute? Okay, sorry.
Thank you. In the top right corner, there's like two rect.
That exoplanet infection, yeah. Like always has to be.
See, that's a, that's insane.
Yeah.
Yes, actually. I guess maybe our discussion is very I'm old, wondering to graduate next year. And who knew? This is Kelsey, our. We definitely more formally introduce. What is it?
It's sharing your.
Yeah. And next year.
Perfect. Very glad.
Yeah. Thank you so much, Riley, for the really cool talk, and now it's my pleasure to introduce our second speaker of the night, Eleanor Greenspoon. Eleanor is a fourth year PhD candidate in physical chemistry at UC Berkeley. She is originally from Seattle, Washington, but came down to the Bay Area for college at Santa Clara University and has been in different parts of the Bay since 2018. Outside of research, she loves running, biking, crafts, and baking treats for her lab mates and friends. Please take it away.
All right, thank you all for hosting me. Like you said, my name's Eleanor. I'm a fourth year grad student in chemistry, in physical chemistry, but I'm in an astrochemistry group. And so today I'll be talking to you about what I'm calling solving cold cases in star forming regions. So what astrochemistry is basically focusing on, in our case, the chemistry that happens from how we get to anywhere from like molecular clouds to fully formed planets to exoplanets, all sorts of different things. And so I wanted to start by just going through briefly the star formation sequence, which consists of, we have a molecular cloud of dust and gas that eventually kind of collapses into the center, which will form later our star. We reach a protostellar stage where there's a lot of active things going on, kind of really violent outflows from the central star, and accreting around the star is this disk of dust and gas, which eventually forms from it associated planets, and eventually a solar system around the central star. And this process occurs in anywhere from 100,000 years to several million years, which in our scales are like really long periods of time, but in astronomical scales are really pretty brief. We go from this kind of diffuse molecular cloud to something like Earth. And so the kind of central cold caves that our group is focusing on is how does chemistry evolve within star forming regions, and how do we see chemistry go from these kind of earliest molecular cloud stages to eventually fully formed planets? Is there chemistry that remains from this like really ancient time, or like what are the processes that happen along the way? And so I have here, like we saw the graphical description or the graphical images of the different stages of star formation, but I thought I would put definitely a lot more beautiful images that we have gotten recently. And so to identify these, and we can kind of tie them to the graphics that I showed earlier. We have here a molecular cloud on the left, the chameleon 1 molecular cloud. We have a protostar in molecular cloud L1527, which you can see those kind of like outflow shapes, this really cool like kind of cone shape around that protostar. And then a lot closer to home, we have Neptune with a bunch of background galaxies, which I just thought this was really cool because like, when have you seen a picture of Neptune like that? Kind of a distance scale. So we have these molecular clouds that are hundreds of light years away, and Neptune, which is approximately 30 astronomical units away from us. So an astronomical unit being the distance between the Earth and the Sun. And all those lovely images are from the James Webb Space Telescope, which many of you have heard of, I'm sure. The really exciting infrared telescope that was commissioned just a few years ago. And beyond just allowing us to have these really beautiful images, James Webb has also unlocked a ton of new information about chemistry. And in particular, James Webb has given us a lot of information about ice chemistry in different kinds of parts of the interstellar medium and of star forming regions. And so this is a really complicated image from the like Webb press releases, but I thought that this was just useful for like showing that this is kind of a spectrum of ice, different species compositions, and showing that like James Webb can give us a lot of information about ices. That's basically what I'm trying to say here. Information that we didn't really have access to before that in the same way when we were using different radio telescopes and other observational techniques. And so I'm focusing specifically on the kind of chemistry that happens during this protoplanetary disk stage. And so to kind of zoom in on that and get like a basic handle on what's the kind of conditions that we're thinking about when we think about chemistry, this is my like simplified cartoon of a protoplanetary disk kind of cut. And so we have our like central star in the center. And kind of coming out from that is like this cone of like I said, like dust and gas. And what's kind of most notable for me when I think about the conditions in a protoplanetary disk is namely the temperature gradients. So right very close to the central star, we have really high temperatures. We're talking like 1,000 Kelvin, thousands of Fahrenheit. And as we kind of move out to the outer edges of the protoplanetary disk, and also as we go towards kind of the mid-plane of the disk, towards like the center line, we get to really, really cold temperatures, like 10 Kelvin, which is like minus 442 Fahrenheit. And so these are really, really cold conditions where this like dust and gas is collecting. It's also experiencing kind of like pressures or like density of molecules that is much, much lower than we have here on Earth, like 10 million times lower than we have here on Earth. And so those are the kinds of like conditions for chemistry that I'm thinking about, trying to figure out how to recreate. And so, like I said, there's kind of dust collecting here. As the protoplanetary disk evolves and planets start to form, we have like dust that kind of condenses into larger and larger chunks, and eventually we reach the planet size. So if I were to like zoom in on one of those little black dots, little pieces of dust, it might look like this is a simplified little cartoon of it. So the dust might be made of like kind of silicate material, maybe carbon-based material. But then we have kind of those like rocky little dust grains, and they're experiencing these temperatures, like I said, like 10 Kelvin, really, really low temperatures. And at those low temperatures and those low pressures, if a gas molecule hits that really, really cold dust grain, it freezes. It like hits and it sticks and freezes. And it forms this like icy mantle around these dust grains. And so these icy mantles are made up of, I think like on Earth, we think of ice as water. And there's a lot of water in these environments. But there's also a lot of other things that exist in the gas phase here on Earth, freeze into ices in these environments. Things like CO2, carbon dioxide, carbon monoxide, ammonia, nitrogen gas. Those are all like mixed together in these icy mantles, interacting with each other and leading to chemistry. Things that can be like kind of further stimulating that chemistry is something like heat. These dust grains are not like static in their spot on the disk. They're kind of mixing around and experiencing like this different temperatures in the temperature gradient. And so that heat, like as we raise the temperature of this mixture of molecules, things can move around easier and they can react. We can also have UV radiation from like the central star or from other stars surrounding this disk. And UV radiation can also stimulate chemistry. As can cosmic rays, if we have impacts from these high energy subatomic particles, that can also cause like a cascade of reactions to happen in these environments. And like I said, with the kind of imposition of all these things, the heat, the radiation, you can have exchange between the gas phase and the ice phase. And chemistry can happen in the gas, and then products can freeze into the ice and the reverse. And we can also, through all these processes, kind of form high energy particles like radicals, which are also like really great at stimulating chemistry, even in really, really cold environments. And so to kind of get more specific about the like research work that I do, the kind of case that we're focusing on is how does chemistry happen even in these really cold, really low pressure environments? And so to look at that, we have to use a couple different techniques because we're looking at a couple different parts of this picture. So we need to focus on the ice itself, how the structure and the composition of the ice changes as we change the conditions, the temperature. We might like try and hit our ice with UV radiation or try and simulate cosmic rays. And we want to measure how the ice is affected itself. But we also want to measure the gas, like as we change the temperature and again, hit it with radiation, like things come off in the gas, we want to measure that as well. And so part of how we do that is with spectroscopy, which allows us to introduce radiation to our ices and record the changes as they're induced, as chemistry happens, as reactions take place and as things change in the ice. So I guess just kind of as a helpful reference, like much of what we think about when we're looking at telescope data is in the area of like the radio, the microwave. James Webb is an infrared telescope, so it's kind of that region of the light spectrum. And then in my lab, we're using anywhere from the visible light spectrum to the X-rays. And so specific end up using is X-ray and Raman spectroscopy to look at what's in our ices, the structure of those ices, how they change as chemistry happens. And then we also use the mass of the gases as they come off of the ices with mass spectrometry to learn about what's in the gas phase. And so we use kind of like a local Berkeley institution for these measurements. The Advanced Light Source Synchrotron at Lawrence Berkeley Lab is where I do all of my experiments. And the ALS is great because they allow us to have like really great, powerful, and like tunable X-rays, which is how I've conducted all my experiments so far. And so a little cartoon of how I conduct those experiments. Like I said, we're talking about really, really low pressure and really, really low temperatures. So we handle the pressure part by building a vacuum chamber with a series of a bunch of pumps that get us down to not quite, but as close as we can get to those like really, really low pressure conditions, like in star forming regions. And then we basically have we use the expansion of helium gas to cool down a surface to 10 Kelvin. We can get down to 10 Kelvin, at least on the temperature front. So we have this really, really cold surface, and then we introduce gas and it freezes out. It hits and it sticks like it does in the interstellar medium. And then once we form that ice, we can do that with water. We can do that with a bunch of different mixtures. We can then hit it with X-rays or with a laser, depending on what the experiments we're doing. And then we can use detectors to record how different aspects of what we change about the ice changes our spectra. And so we can also change the temperature. We can, like I said, like introduce radiation, and we can try and simulate different kinds of chemistry. So this is a little cartoon, but I thought it would be fun to show what this looks like in real life. Which is like similar, you can see our kind of spherical chamber, but it involves kind of a lot more. But yeah, so that's what this looks like in real life. This is at the advanced light source of that LBL right now. And this is just like a sample of what like our data looks like. This is water ice. So we just formed just a pure water ice at 10 Kelvin, and then we heated it up. We took a bunch of measurements as we heated it up. This is great because I think it was kind of a pretty simple experiment. It's just water. We didn't do much to it besides warm it up, but you can see that there are changes. And so focusing on like different parts of our spectra show us different things about the water ice. This kind of like low energy portion here shows us that we're actually forming products as we're hitting our ice with radiation, and then heating it up, we're forming products, drops from the water. This region is relatively boring in water ice. It can tell us a lot about like what the species is that we're actually looking at. And in this case, we know it's water and it's just water. But it can also tell us about the charge or kind of how the different atoms that we're looking at are arranged. And more with that, this kind of end of it can tell us about the structure of our ice. And so you can see little changes here. The kind of pink, like warmest part of that looks a little bit bumpier than the rest of it. And that's telling us that our water is going from a like disorganized low temperature arrangement to a crystalline arrangement, more like how we're used to water on Earth. And so that's kind of one result, or like one piece of the puzzle of this kind of problem that our group is looking at about how do we understand chemistry in these environments. So I thought I would give like an ending little case update status on our cold cases. Because James Webb gives us a lot of new information and a new method of studying chemistry of star and planet forming regions. But to really understand those really complicated spectra that I showed at the beginning and kind of get an idea of what's actually happening, we need new lab techniques on Earth. We need to kind of simulate these environments and do our best to understand precisely what's going on. And my work has focused on building new techniques to study the kind of ice structure and the ice properties as chemistry is happening. And so with that, I thought I would acknowledge my group because that big instrument was like, did not exist 3 years ago. And I definitely didn't build it alone. So this is my group at Oakland Ballers game with Scrappy. This is Jenny Bergner, my PI, who has like been obviously incredibly helpful in allowing me to do this. Also, we had a really great collaborator, a B-Mind scientist at Lawrence Berkeley Lab, Ms. Ahmed, and everyone else in my group helped me. But yeah, thank you. That's all I have. Thanks. Yeah.
This is just a totally like ignorant question about how to read that graph. The like spectrum graph at the very low energies when you were describing how, I think it was as you increase the temperature, you were saying we can see that there's some like products or there's some,
Yeah.
how does that how does like the lowering of those peaks indicate that there's some like interactions happening?
Yeah, totally. So what we got that from was actually just comparing to like previous work on different water ices and different like molecules, like I said. So seeing the kind of structure of this like this feature change like with the changing temperature, and as we like introduced more radiation to it, we kind of compared that to like previous work on different mixtures of things and saw that those kind of peaks were signifying that there were different like products forming as like we just imposed the like X-ray beam on the ice. Yeah.
Can you tell us a little bit more about what the process was like building?
Yeah, that is like what I spend the vast majority of my time doing. I was doing it today, because we're making a bunch of changes to it. So I think like the major difficulty is like getting these pressure conditions. I said that we're like not actually doing it. We're just kind of doing the best we can, but we have to incorporate a lot of different components in order to do all the measurements we want to do. Which involves like making a lot of attachments to like our central chamber. So I think if we had a perfect like sealed off just like our sphere, we would be able to get to really great pressures. Things would stay really clean, and we would do a lot better job of like mimicking the conditions. But in reality, we just put this big detector on right here, and then turned on all our pumps, and like our pressure was like an order of magnitude worse than it was when we did our experiments without it. And so a lot of work goes into checking for different leaks and like incorporating different kind of schemes of kind of pumping, and just like kind of trying to be clever about like how can we get as much out of this, like both our like little setup with our kind of cooled surface where we want to form the ices, like how can we like get as much information out of that as possible, without compromising pressure, which sometimes we have to. But yeah, that's a little bit of it, I guess. Yeah.
Could you go back to the next slide where you have this, like, yeah. I don't know anything about plasma energy. And so outside of this range that you've shown, do these samples kind of just are not distinguishable, or do they also have different?
Yeah, so the reason we choose the kind of like range that we do is that this like range around 500 to 600 corresponds to the area where like a certain like there's a certain absorption of light by the oxygen atom. So we're focusing on oxygen because it's water. And this region is like interesting to oxygen specifically. And so in different mixtures of other ices, we would focus on like different ranges. I've spent a lot of time looking at like nitrogen water ice mixtures. And then we look at this range, this like 500 range, to be like, okay, what's happening at the oxygen level. But then also we look at the like 400 electron volt range to be like, what's happening at the nitrogen, because that's where the nitrogen absorbs. So like for water, there's not much interesting going on elsewhere, but if we were to look at other things, there totally would be. Yeah.
Would you expect the ice in these conditions to be like super light, like not dense at all? Like I just can't imagine
Yes.
something that low.
Totally. I wish I should have included a picture, but so the ice like at this low temperature, low pressure is like amorphous and like very like fluffy, porous. Like in my head, and this is totally like not accurate, it's like the difference between like an ice cube and like a snow cone. Is like how I like rationalize it in my head, but like on a really small scale. So it's really fluffy, it's really porous, and it's like randomly organized.
If there are no more questions, let's give Eleanor one more round of applause. All right. Thank you everyone for coming to tonight's wonderful Popping in the Science Bubble seminar. Our next seminar is going to be November 18th in just about a month's time, where we will be learning all about, if this will cooperate, there we go. Well, we'll be learning all about quantum computers, and we'll be learning all about the immune system and cancer. This one will be at the West Branch, as I had mentioned before. So please come on out for that. And if you want any more of our, if you want to stay tuned, you can either look at this. You can scan this QR code. This is a link to our YouTube page. We also have our website here that has all of our previous seminars archived as well. So we hope to see you again in just about a month's time, and thank you so much again for coming out. We hope you have a wonderful evening.
This is really great speakers tonight, very interesting topics. Thank you so much.
Yeah.
It's